there, guys. We're going to be doing the mole unit. Start the mole unit now. Let's see. There we go. We're at the beginning of our note. This is on the mole. And the mole is not something on your aunt's face. It's not a little fuzzy animal underground. It's actually a counting number. It's something that chemists use to count really, really small, tiny things. So let's go ahead and get started. In chemistry, it's often necessary to accurately count the number of atoms, molecules, or formula units in a sample. But since these things are so terribly, terribly small, we need a very, very large number to count them. So we use something called Avogadros number. Avogadros number is equal to 1 mole of any substance. So 1 mole of anything is Avogadros number. So Avogadros number you see there is 6.02 times 10 to the 23rd, which is a whole lot of anything. But that's what we use to count really tiny things like electrons or atoms. A mole is something that's used to specify a particular quantity. Okay, it's the SI unit based for the amount of substance. Its abbreviation is MOL, which is not a whole heck of a lot smaller than MOLE, but it's MOL. Don't use just M. Don't use anything but MOLE or MOL. Okay, but that's just the abbreviation is MOL. Doesn't mean molecule, so be careful. Like I said, the mole represents a quantity. It represents a really large quantity, 6.02 times 10 to the 23rd. So what are some other things that you can think of? So words that mean a number, words that mean a quantity. The first thing that comes to mind for me is eggs. How do you buy eggs? You buy eggs in a dozen. Well, how many is a dozen? A dozen is 12. So you know that a dozen, when somebody says a dozen, they mean 12. How many do I mean when I say a pair? Like a pair of shoes. Well, that's 2. Okay, there's a lot of words that mean quantities, and that's all that the mole is. It just is a word that means an amount. 1 mole of anything contains 6.02 times 10 to the 23rd of whatever that is. So a mole of eggs would be 6.02 times 10 to the 23rd eggs, and so on and so on. A mole of iron is 6.02 times 10 to the 23rd atoms of iron. A mole of iron oxide would be 6.02 times 10 to the 23rd formula units of iron oxide. Be careful. Remember that formula unit is the word that we use to describe an ionic compound, which is a metal with a nonmetal. Okay, so we're going to watch this video real quick. Doesn't take very long, but it's really kind of interesting. So enjoy.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadros number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole. Avogadro, basketballs, and how to buy salami at the grocery store.
So that was fun, right? A mole is a really big number. So my favorite is a mole of pennies. That would be great. I think that would be the best. Okay, so back to representative particles for a second. Particle types used in chemistry depend on their substance type. Remember that we gave certain names to certain substances. So elements, we call them atoms, like an atom of iron or an atom of sulfur. An ionic compound is a metal bonded to a nonmetal, and we call those formula units. A covalent compound is 2 or more nonmetals bonded together, and we call those molecules. Some elements don't exist naturally as single atoms, but they exist as diatomic molecules. Remember, those are the Brinkelhoff atoms. Those are the atoms that can't exist alone. Oops, sorry, went too far. Go back. Diatomic molecules are composed of 2 atoms of the same element. Now, diatomic molecules are these that are listed here. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So all of these, when they're by themselves, they get a subscript of 2. And we talked about that when we were writing chemical reactions. Brinkelhoff is just a weird word that we made up. That has all of the diatomic elements in it. Okay, if you can remember the weird word Brinkelhoff, you can remember, look, see, all of those are the diatomic molecules. Okay, so those are diatomic Brinkelhoffs. So what do we call potassium? Okay, the formula for potassium is just K, right? What type of substance is it? Well, if it's just potassium, it's just going to be an atom. It's an element. And how about magnesium chloride? Magnesium's a metal and chlorine's a nonmetal. So do you remember the formula? MgCl2. What substance type is that? Well, that's an ionic compound. Okay, and we call that, formula unit. Diphosphorus pentaoxide. Okay, well that is going to be P2O5. Remember, for covalent compounds, you get to use the prefixes, and the prefixes tell you the number of atoms of each one of those elements in the compound. And as I said, it's a covalent compound. We can call those things molecules. Fluorine is one of the Brinkelhoffs. It's one of the diatomic molecules. So its formula is F2 because it doesn't exist alone. It's a diatomic molecule, and again, we can call that a molecule. Okay, so when we're doing these conversions for the mole, we gave you the equality earlier that 1 mole of anything is equal to 6.02 times 10 to the 23 of that thing. When we're using dimensional analysis to do these conversions here, we can use 1 mole over 6.02 times 10 to the 23rd particles, or we can flip that to use it in any way we like. Remember dimensional analysis? You hated it before. You're going to hate it again. But that's okay. It's going to be really useful now. Okay, so what we're going to do is we're going to calculate, we're going to determine the number of particles in 7.5 moles. So we're going to go from moles to representative particles. So let me see if I can't get this working here so I can write on my screen. Okay, yeah, I think, there we go. Oh, yep, there I am. Okay, so remember dimensional analysis. You have to start with whatever you're given. Well, in this case, I'm given 7.40 moles of sulfur dioxide. So I write 7.50 moles of sulfur dioxide. And the formula for sulfur dioxide, SO2. So I'm going to convert that into particles. I've got moles and I'm going to particles. So recall from dimensional analysis that we disco down the unit. Yeah, you have to hear that again. I'm going to say that like 1,000 times. Disco down the unit. Well, the mole of SO2, that's my unit. So I write moles of SO2 in my denominator. In the numerator, I write the other part of my conversion factor. Okay, so on top, I'm going to representative particles. So how many representative particles is in a mole? Well, that's Avogadros number, 6.02 times 10 to the 23rd. And SO2 is a covalent compound, so we can call those molecules. There we go. Okay, so 7.50, I disco down my unit so I know where to go. I put Avogadros number of particles on top, 1 mole on bottom. Okay, I'm going from moles to particles. I cancel my units. Okay, I'm left with molecules. I've got Avogadros, I've got the representative particles that I'm looking for on top. So I stop and I do a little bit of math. I multiply 7.50 times 6.02 times 10 to the 23rd. And I get, okay, it took me a minute to do my calculation, not 7, just kidding. If you were doing that and you saw me write 7, don't worry, it's all right. 4.515 times 10 to the 24th molecules. Okay, remember sig figs? You hated that too, so that's okay. We're going back to it again. How many sig figs is in this? Is in my given? 1, 2, 3. Remember zeros, final zeros to the right of the decimal point, or ending zeros. If there's a dot, endings are significant. So look, there's 3 sig figs here. I need 3 sig figs here. There's 1, 2, 3. So that 5 is the only thing that I'm allowed to use when I'm rounding. So what does that 5 do to the 1? Right, it rounds it up. So my final answer is 4.52 times 10 to the 24th molecules. Okay. All right, we're going to do this next one, 0.400 moles of potassium chloride. So I'm going to use my conversion factor. 1 mole equals 6.02 times 10 to the 23rd. So I'm going to use that down here. I start out by writing my given. Let me see if I can get down here far enough. 0.400 moles. Potassium chloride, how do I write that? KCl. So, what do I do now? Oh yeah, you know it. I disco down that unit. Put moles of KCl in the denominator. Okay, this is my conversion factor. What number's next to moles? 1. So what do I put on top if I'm looking for particles? Avogadros number. 6.02 times 10 to the 23rd. And what do we call KCl? What's its name? Is it a atom, molecule, or formula unit? Well, it's an ionic compound, so this is a formula unit. Okay, so equals, let me there we go. Okay, I cancel out my units because they're diagonal from one another. So I multiply 0.400 times Avogadros number divided by 1. Let's see what that is. 0.400 times 6.02 times 10 to the 23rd gives me, let me find my pen here, 2.4, ooh, hey, that didn't work, 2.408 times 10 to the what? 23rd. To the 23rd. Okay, sig fig it. How many sig figs can I have in my final answer? Well, over here, beginning is never. So beginning zeros are never significant. So that doesn't count. Ending is 0 if there's a dot. So all these ending zeros here are significant. So there's 1, 2, 3 sig figs in this answer. So I can only have 3 sig figs in this answer. 1, 2, 3. What does the 8 do to the 0? It rounds it up. 2.41 times 10 to the 23rd. And it's formula units. We're going to use F formula units of KCl. Good? Okay. Alrighty. So let's go to the next one. Let's go to the next slide. Okay, so next slide. There we go. All right, so we've got another one that we're going to do. We're going to find the number of moles in the following. So in this case, we're going backwards. We're going from particles, which are atoms, to moles. All right, get my pen going here again. So this is my given. I'm going to write out my conversion factor. 1 mole of anything equals 6.02 times 10 to the 23rd of that thing. So down here, this is my given. I've got particles. So I write 4.81 times 10 to the 24th atoms of lithium. So what am I going to do? I'm going to just go down that unit. The atoms of lithium in my denominator. So that is my particle. So atoms, in front of atoms, I put Avogadros number, 6.02 times 10 to the 23rd. Okay, what else do I have? Well, up here I have moles. Okay, I've used this, so I'm going to use moles now. It's going to equal 1 mole of lithium. So in 1 mole of lithium, there's 6.02 times 10 to the 23rd atoms of lithium. So in this way, we're going to go from atoms to moles. So I can cancel out these units, okay, and multiply. I'm going to multiply 4.81 times 10 to the 24th times 1, and then I'm going to divide by what's in the denominator. So I get 4.81 times 10 to the 24th divided by Avogadros number, because that's what's in the denominator. Okay, let me do a little bit of math here. 4.81 times 10 to the 24th divided by 6.02 times 10 to the 24th, and I get, where am I, 0.799, oh wow, big number, 0.03322 moles. Okay, how many sig figs can I have in my final answer? 3. So 1, 2, 3. Does that 0 round that 9 up? No, it doesn't. So my final answer, 0.799 moles of lithium. Okay, let's try this one down here. We're going to use the same conversion factor up here. 1 mole is equal to Avogadros number of any particle. So we go back down here. My given is 3.4 times 10 to the 26 molecules. Molecules is a particle. Okay, so next I just go down my unit. My unit is molecules of nitrogen dioxide, sorry. So I put molecules of NO2. Well, since that is a type of representative particle, I'm going to use Avogadros number next to it. So 6.02 times 10 the 23rd. Okay. What's equal to 6.02 times 10 to the 23rd? 1 mole. 1 mole of anything. In this case, it's going to be 1 mole of nitrogen dioxide. So I get to cancel my units because my units are the same. They're diagonal from one another. And I multiply everything in my numerator. So this is going to be 3.4 times 10 to the 26th molecule, or I'm sorry, nope, not molecules. It's 3.4 times 10 to the 26th times 1. I'm an idiot, sorry. And below, divided by Avogadros number, 6.02 times 10 to the 23rd. Okay, 23rd. Okay, so when I do that division, 3.4 times 10 to the 26th divided by 6.02 times 10 to the 23rd, I get fairly reasonable number, 564.784, blah, blah, blah. There's a whole bunch of numbers back there. But how many sig figs can I have in this answer? I can only have 2, so I go back here. 1, 2. So does that 4 round the 6 up? No, it doesn't. It leaves it alone. So this answer, and that 4 doesn't go away. You don't round 564 to 56. You round 564 down to 560, right? 560 moles NO2. Okay? What do you think? Terrible? Hard? You'll get plenty of practice. It'll be fine. All right, so molar mass. Let me remind you what molar mass is. And it's a pretty easy thing to use. 1 mole of carbon, for instance, if you look on your periodic table, the mass that's in the box for carbon at the bottom is 12.011. So 1 mole of carbon atoms, the 6.02 times 10 to the 23rd atoms, equals the molar mass on the periodic table. So 1 mole of carbon is equal to 12.011 grams of carbon. Molar mass is the mass in 1 mole of any element or compound. The units for molar mass are grams per mole, or G/mole. It's the molar mass of any element equal to its atomic mass from the periodic table. Sounds complicated, but it's really not. So let's do some molar masses here. Okay, in order to do these molar masses, kids, we're going to need the periodic table. So make sure that you have your periodic table handy. All right, you're going to need it handy. So what I want you to first do is I want you to find zinc on your periodic table. Okay, it's a transition metal. It's up there in the top right corner of the transition metals, though. It is a it's an exception. It's in that exception block. So find zinc and look at the mass underneath it. The molar mass of zinc is 65.38 grams per mole. That's it. Find chlorine. Now, what's the formula for chlorine? It's Cl2, isn't it? So the molar mass of chlorine is going to be its mass on the periodic table, 35.453. Yep, you guessed it, times 2. Okay, what is that? Okay, use your calculator. 70.906. And the unit, G/mole. So let's go up here to calcium bromide. We need to write the formula. The symbol for calcium is Ca. The symbol for bromine, Br. Calcium's oxidation number +2, bromine -1. So we crisscross those, make them subscripts. The formula is CaBr2. So to find the molar mass of this thing, you do calcium times 1, bromine times 2, and then you're going to add those together. So find the molar mass of calcium on your periodic table. It's 40.078. But since it's times 1, it's just that mass. Find bromine now. It's a halogen. Bromine, 79.904 is the mass. But since there's 2 of them, you have to multiply by 2. So 79.904 times 2, 159.808 is what I get. 159.808 grams per mole. That's the molar mass of calcium bromide. So let's go magnesium phosphate. Lots bigger formula. The symbol for magnesium is Mg. Phosphate, since it's ATE, that means it's a polyatomic ion. So you find that on your list of polyatomic ions, and it's PO4. Oxidation number for magnesium is +2 because it's in group 2. Phosphate is listed on your in your polyatomic ions, and it's a -3. It has a -3 oxidation number. So I crisscross, make them subscripts. The formula is Mg3PO4 2. All right. So I did this one because I want you to see what that 2 does. The 2 gets distributed to both of these. So that would give me 2 phosphorus and 8 oxygens when we're calculating molar mass. So magnesium is going to be multiplied by 3. Phosphorus is going to be multiplied by 2. And oxygen is going to be multiplied by 8. Oh, times 8. Duh. Times 8. So magnesium, find that on your periodic table. It's 24.305, and we're going to multiply that by 3. So it should be 72.915. Okay, next find phosphorus on your periodic table. Its molar mass, 30.974, and I'm going to multiply that times 2, and I get 61.948. Okay, last we're going to do oxygen. Oxygen's molar mass is 15.999, and I multiply that by, what is that? 8. Multiply by 8. 127.992. Okay, so you add all 3 of these guys together. Add them all together. So it's going to be, let's see, 72.915 plus 61.948 plus that molar mass of oxygen gives me 262.855. And the unit is grams per mole. Okay, molar mass. Molar mass, not hard. Molar mass, not hard. All right, so conversion factors. Now we're going to use conversion factors because we can calculate the number of grams in a mole. Okay, we just did that actually. The equality that we're going to use though in this case is the number of grams is equal to 1 mole. So the conversion factor we'll use is the molar mass that we get on the periodic table, the number of grams over 1 mole, or vice versa, depending on what it is that we're trying to calculate. I'll show you. So in this case, we're going to use 1 mole is equal to the molar mass. Okay, 1 mole is equal to the molar mass. So you'll find this on your periodic table. All right. We're going to find the number of grams of the following. This thing needs to be out of my way. I wonder if I can move that. I sure can. There we go. So I'm going to take 2.50 moles of sodium chloride, and I'm going to calculate the molar mass. I start by writing 2.50 moles because that's my given. 2.50 moles of sodium chloride. Okay, before I do anything, I just go down the unit. Put moles of sodium chloride, O-L, NaCl, in the denominator. Okay, up here, what number is next to mole? 1. Okay, what's the other part of that conversion factor? Molar mass. Well, molar mass of what? What do you think? Molar mass of sodium chloride. So I need to find the molar mass of sodium chloride. Sodium chloride is made up of 1 sodium plus 1 chlorine. Okay, NaCl. So the molar mass of sodium, 22.990, plus the molar mass of 1 chlorine, because that's all that's in the formula, 35.453. So add those two things together, 22.990 plus 35.453. And I get 58.443. 58.443 grams. That's the molar mass. That's the mass of sodium chloride. So I'm going to use that right here. 58.443 grams of sodium chloride. So I multiply everything in my numerator. I got to cancel my units first, sorry. Multiply what's in my numerator. 2.50 times 58.443 And I'm going to divide by what? What's in the denominator? That's just 1. So 146.1075 divided by 1, which is equal to 146.1075. Okay, how many sig figs can I have in my final answer here? How many do I have in my problem? I have 3. So 1, 2, 3. Does that 1 do anything to the 6? No, it doesn't. So my final answer, 6 grams in sodium chloride. Duh. Sodium chloride. That's the number of grams in 2.5 moles of sodium chloride. Okay, let's try 1.70 moles of calcium hydroxide. Oh, gives me a little bit more space. I like that. 1.70 moles of calcium hydroxide, CaOH. 2. Why? Because calcium is +2. Hydroxide is a polyatomic ion, -1. Crisscross applesauce, and you get CaOH 2. So in 1.70 moles of calcium hydroxide, I want to know what the mass is of 1.70 moles of calcium hydroxide. So I write my given, then I just go down that unit, put moles calcium hydroxide in the denominator. Okay, I'm going to use my conversion factor. 1 mole is equal to the molar mass. So 1 mole of calcium hydroxide is some molar mass. We'll have to find that out. See, there's 1 calcium. So calcium is 40.076. How many oxygens are there? 2. So oxygen times 2 is 15.999 times 2. 31.998, and hydrogen times 2. It's 1.008 times 2, 2.016. So I'm going to add all those together to get the molar mass to go right here. All right, 40.076 plus 31.998 plus 2.016. Okay, that gives me a syntax error. So let me try again. Let me put my pen down. Try again. 40.076 plus 31.996 plus 2.016. That's a 6 is there. Oh, 31.998. Just kidding. You know what? If I would quit getting syntax errors, this thing would move right along. You probably have already added them all together, but your teacher is having calculator difficulties. Actually, it's not calculator difficulties. It's operator error today. Just to tell you the truth, it's operator error. So, let's see. 74.09 is the, add them together, it's 12. Yep, that's right. 74.09 is the molar mass in 1 mole of calcium hydroxide. So I'm going to put that right there, 74.09 grams. That's the molar mass in 1 mole. So I can cancel my moles, cancel my units there, multiply everything in the numerator. So 74.09 times 1.70 gives me 125.953 divided by 1. Yep, divided by 1, that's it. Equals 125.953. But how many sig figs can I have? Yep, 3. 1, 2, 3. What does that 9 do to the 5? Right, it rounds it up. So my final answer, 125.6 grams calcium hydroxide, CaOH 2. Okay, so that's the conversion. Ooh, let's see if I can get it even smaller. How does that, let's see if we can't go back. Yeah. Here, let me pause you for a minute. Okay, thank you for that pause. I paused me and I fixed my screen. So there you go. That's why it looked like magic occurred. It did not. Okay, so let's go backwards. Let's go from grams to moles. Let's find the number of moles. So let's see. We're going to use one. Oh, yep, just kidding. We're going to use that. And we're going to go back a slide. There we go. Let's try this. All right, there we go. We are going to use 1 mole is equal to the molar mass of the substance. Okay, so down here we've got the mass of potassium sulfide. So I write my given, 74 grams potassium sulfide. It's a 7, by the way. Just doesn't look like one. 74 grams of potassium sulfide. I just go down the units so I know what goes where. So grams of K2S go in the denominator. Well, up here, molar mass, okay, so I need to find the molar mass of potassium sulfide. So I go over here and I know that there's 2 potassiums, so K times 2, and there's 1 sulfur, sulfur times 1. So potassium times 2, you find potassium on the periodic table and it's 39.098, and you multiply by 2, and it gives you 78.196. So 78.196. And then sulfur times 1, okay, sulfur on your periodic table, 32.066. Then you add those together. So plus 32.066, and I get 110.262. Okay, that's the molar mass in 1 mole of potassium sulfide. So I'm going to go over here and put that in here. 110.262 grams in 1 mole of K2S. So I can cancel my grams, and I multiply everything in the numerator, which is 74 times 1, and I'm going to divide by whatever's in the denominator, 110.262. Okay, when I do that math, 74 divided by 110.262, I get 0.6711. Oh my gosh, too many numbers. 28766. How many sig figs can I have in this answer? Right there. 2. 1, 2. Does that 1 round that up or leave it alone? Right, it leaves it alone. So my final answer, 0.67 moles K2S. Okay, 205 grams of carbon tetrachloride. Well, I'm going to use molar mass and mole. I'm going to use that again. I've got grams. So I go down here and I write my given. 205 grams carbon tetrachloride, CCl4. Okay, I set up my dimensional analysis. I need a conversion factor. I'm going to disco down the grams of CCl4, okay, because that's my unit. So molar mass went on bottom, so that means 1 mole goes on top. 1 mole CCl4. I need to find the molar mass of this to go right there. So 1 carbon is 12.011, and 4 chlorines is going to be 35.453 times 4. It's a lot. 141.812. 141.812. Then I'm going to add these two together. And I get 153. I'll put it down here. 153.823. 823. There. So I multiply everything in my numerator. 205 times 1 is 205. Only thing that's in my denominator here is 153.823. Divide denominator into numerator. 205 divided by 153.823 gives me 1.3327 plus a bunch of other numbers. But how many sig figs can I have? 3. 1, 2, 3. So that 2 is the only thing that I can use to round anything. 2 does not round that 3 up. So my final answer, 1.33 moles carbon tetrachloride. Okay, so rewind, use this again if you need to, whatever you got to do, and we'll move on to day 2 next.